A wonderful morning. I'm glad to introduce today's last session of the week. In the week, we have already heard about our products, our overall company, the second session, which was held on testing, and the third session, which was the first material card generation session. Today, we will be summarizing these topics, and we will give you a short outlook, and we will deal with any questions in the latest part of the session today. So without further ado, I would like to welcome my colleague, Mr. Stefan Rimmelmoser, who will be summarizing the session from Wednesday, I'm sorry. So, Mr. Rimmelmoser, welcome.
Hello to everybody from my side here from this wonderful sunny Friday morning. It's a pleasure to summarize my session from Wednesday with the topic of the efficient dynamic testing. I will give you the rough overview about our hardware. Everybody who joined the first session on Wednesday knows this slide. Here you can see the development of our testing system IMPETUS. You see the development from the right upper side to the left down side. It's a development over the 15 years, which was increasing the hardware every time. First, I will talk a little bit about the IMPETUS itself. The IMPETUS itself, it's a desktop testing device. What does this mean? The IMPETUS is a testing device which don't need a further infrastructure. For example, on a big dynamic testing machine, on a servo-hydraulic testing machine, for example, you always need a really good fundament and a really stiff floor to set it up, and you also need some strong power supply or something like that you can use a high dynamic testing machine. And our testing machine, it's also really doing dynamic testing, and therefore we can just put it on a table, and this is the big advantage of the testing system IMPETUS, I think. To the characteristics of the IMPETUS testing system, we can reach 50 joule of impact energy. What does this mean? The impact energy depends mainly on the mass of the swing hammer, which came up from 1.5 to 5.5 kilogram. And it's also depending on the impact velocity, where we start with 0.5 meter per second and can rise up to 4.4 meter per second. And with this combination, we are able to reach 50 joule. As you can see, our testing device has a dimension of about 1,400 to 600 to 850 millimeter. This is roughly that big as a standard transport pallet. And our testing device has a mass of itself of about 165 kilogram. So you're able to rise this, to put this testing device up on a table with 4 strong people, I think. And this is the big advantage, that you can just put the testing device IMPETUS on a strong table or on a workbench, I will prefer, and you can test without further infrastructure. Sorry. And the big advantage of the system also is that we're just using a normal power supply, so we don't need extra strong power supply or something like that. We're using the normal current values of electricity. As you can see on the left side of the pendulum, here on this picture, we have mounted the high-speed camera, which is a really cool advantage, I think, that we can just mount the high-speed camera on fixed positions, and also can trigger the high-speed camera that we have a time synchronous data from the high-speed camera and the measurement data. But on this topic, how we deal with high-speed camera, with external data and with the measurement data from the pendulum, I will talk about next week on Wednesday, more about that on Tuesday, sorry, more on that topic, because I will show you the dynamic tensile test, and there I will go deep in detail how we are measuring with DIC images from a high-speed camera and combine it with the measurement data from the pendulum. So I'm really looking forward to this session. This slide I really like, because this slide shows really good how big the possibilities to test, how big the possibilities are to test with our impetus. We have divided the configuration of our system into three main configurations. We have the basic configuration on this side. This includes the 3-point bending and the compression test. The standard package of our testing device also includes a tension bending test. In the tension bending test, we fix the sample on each side and perform a bending test. That means that we start in a bending dominated load case and go further into tension. So you can investigate your material under tension behavior. Also included is the puncture test, which in this puncture test we investigate failure of the material under a triaxiality, and we also have a component test where we can test big components to validate our material card on real components. And quite interesting is the sample magazine, where we can perform 3-point bending tests on high and low temperature. And the professional package includes also the tension test, which I will show you on Tuesday. Now I will show you a short video of our testing system, where you can see how the main workflow is through testing with impetus. Here you see a good look to our 3-point bending, to the tension bending, and to the compression test. Here's a component test. It's a 3-point bending with small components, and the tensile test. Now you will see how we perform a test. Christoph, the video was stopped. Now we continue. As I've mentioned before, it's a really universal testing machine. So we're starting just with bending, but developed every new setup. Here we put in a bending sample. We have to close the safety screen and rise up the arm to the decided velocity. The arm stops on the high, what we have decided before. Just once again. Now we can push the green button. The pendulum arm hit the test piece and the data was saved. You can directly see the data in the software we have evaluated, and you got, for example, the force displacement or the stress strain curve directly after the test. Okay, so I hope it shows you the main workflow, how we operate with our system. This slide, I will show it to you because you always have to think about your material class, what you like to test, because the material class depends on what test you can perform. So if we think about a plastic test sample or a thermoplastic material, for sure you can perform a 3-point bending test, a tension bending test, a puncture test, and a tension test. But you always have to keep in mind the dimension of the samples. And in special, you always have to think about the thickness of the sample. For foams, we do compression tests for sure. So we can investigate the compression behavior of foams in the really high dynamic range. Composite will be tested on puncture tests and for sure on 3-point bending. And here the last two materials are aluminum and metals. For sure we can test aluminum and metals with our system, but there are slightly different between aluminum and metals. Aluminum, we also can investigate the deformation behavior, and we reach failure here in the tension test or in the tension bending test. But on metals, it's hard to reach failure. So it's quite investigating the just the deformation behavior, because we have not that much energy for metals. This slide shows you our injection mold for plastics, what we are using for the standard characterization of plastics. On the right upper corner, you see the plate, the standard ISO plate with a dimension of 120 to 82 millimeters. This plate we are using for fiber reinforced plastics, because out of this plate we can just mill out our samples in each direction what we want to investigate. When we are using this plate, we are using also for the puncture test. And this right plate is the component plate. Here you see the tensile test piece and a component. In this component is called the X-rib, where we can validate our material card. The left side there you can see a plate with different thickness of this material, and we have a melt and weld line plate. Okay, and now the last point I will show you today is a little bit about the measurement technique of impetus, what we are measuring. In the tests, we are using two acceleration sensors. One sensor is mounted on the pendulum head and one on the counterbearing side. So we don't measure directly the force. We are measuring the acceleration of the pendulum head and can calculate out of the mass of the pendulum head multiplied by the acceleration, we calculate the force. The third sensor what we are using is an angle sensor. It's on the top of the test system. This angle sensor can give me a displacement with a really accurate, really big accuracy. So we are reaching about 0.01 millimeter. For sure, we have a bending fin and a support with a radius of 2 millimeters in the standard. We can change it to a 5 millimeter radius if we want. And as I mentioned before, we have a swing hammer mass of 1,580 gram. This could be increased by adding some additional mass. And when I add some additional mass, I raise the swing hammer mass, and so I got more energy, more impact energy. And this slide shows you the raw data of the measurement system. It's important to know that we always store the complete unfiltered raw data in our database, so you are able to change the filter and to evaluate the test data again and again. But this topic I also will talk about on on Wednesday in detail. The red curve is the acceleration curve of the swing hammer. The blue curve, it's nearly a zero line, is the acceleration signal of the support. This support acceleration we are using just to check if everything is fixed in the pendulum, because when the counterbearing system is not fixed, you will get an acceleration signal on the counterbearing, and you knew that something was going wrong in the test. But with this zero line, it looks good. And the third channel, what we are here, is the channel of the angle signal, which is decreasing from falling down from the pendulum arm. Okay, and the last slide today is just our results from a 3-point bending, a tension test, and a puncture test, where we combine in blue a dynamic test from IMPETUS and a static test from any universal testing machine. And this slide shows you the big advantage of the dynamic tests with IMPETUS. These results are from a thermoplastic material, and it's a really typical thermoplastic result. You can directly see out of the measurement results the big influence of the velocity of the strain rate, I will say. So we are not just rising the force level, as you can see here in the bending. We also got a stiffer response in the stiffness over the velocity. This is the viscoelasticity and the viscoplasticity here in the force level. And not only the deformation behavior changes over the strain rate, also the failure changes in the strain rate. So we got an earlier failure in higher strain rates. And this all you can see directly out of the measurement results. So we'll really thank you for your for this session and wish you all a nice weekend. We will see you again on Wednesday. And now I will hand over to my colleague, Harish. Thank you.
Hello, everyone. Again, to all the audience that are listening from all over the world, I say hi again. You have seen me yesterday. Today, I will just summarize what we did yesterday and then go a little further into introducing what we will be doing next week on a more complex material model. Okay, so just a general overview. So in LS-DYNA, we have around 265 material models implemented. In our case, for a plastic material, it usually comes down to, in our case, in the plastic material, we have the most used material model, which is the MAT24, which we talked about in detail yesterday. And then there are other interesting material models for a thermoplastic polymer, such as MAT124, MAT187, MAT187 light. So what exactly are all these material models and why you should think about using them? Okay, so the MAT24, the workhorse, we spoke about it yesterday. We had a session where I showed you how you could fit a elastic viscoplastic material model for a polypropylene material. So just to have a summary or just to look back, so what is the MAT24 material model? It is a material model with a von Mises yield surface. You cannot define viscoelasticity with this model. Viscoplasticity is included. There is no tension compression asymmetry because of the von Mises definition, and you have the plastic Poisson's ratio of 0.5. So what does a plastic Poisson's ratio of 0.5 mean? It means that we have plastic deformation under a constant volume. sorry. So for all our listeners who have worked with plastics, they know that this last line with a plastic Poisson's ratio of 0.5 for a very ductile material is more of an assumption than it is what's happening in reality. So that is precisely why we have all these different material models. So the first one is a model that is surprisingly overlooked by a lot of members in the plastics community, which is the MAT 124. So my colleague here, Mr. Reithofer, named it appropriately the hidden material model. Why do we say it's hidden? Because you can define compression tension asymmetry by using two von Mises yield surfaces. One big advantage is that you can define viscoelasticity using a Prony series. But the major problem still remains with this plastic Poisson's ratio of 0.5. Then we go to the model, which is called the plastics expert. So MAT 187 or MAT SAMP1, as it's well known. Here, it's a highly accurate material model because we have different definitions for the yield surface. So we can define a yield surface in a linear way, as a parabolic surface, or even in a piecewise linear surface. Viscoelasticity is included. You can define your Young's modulus as a function of your strain rate. That is possible. Viscoplasticity is included. Compression tension asymmetry is also included. You can incorporate that in a lot of different ways using the Drucker-Trager yield surface or even a general yield surface. But by far, the biggest advantage here is that you can actually define a plastic Poisson's ratio, which means that you can take volume dilatation into account, which for a ductile material becomes very important. We will have a very detailed look on this material model next week. So two of my colleagues here will talk about that. So now I've told you the good about MAT 187. Now it's time to come to the disadvantage. The biggest disadvantage is because this model is so accurate, it is so well formulated, the biggest problem comes with the computational effort. So by far, out of these three models, MAT 187 is computationally the most expensive material model. LS-DYNA has recognized that, and they have provided us with a new, it's called MAT 187 Lite, very aptly named because it's an efficient version of the MAT 187. So the one simplification that they have taken into account is the yield surface. You can define it linearly. You can, of course, define compression tension asymmetry and also take volume dilatation into account. So if you see these two rows, you can easily make out that it's a light version. It's very efficient, and you get very similar results as for MAT 187. It's included since version 12. Okay, now I would what I would like to show very shortly. I know it's a Friday morning here, so I don't want to run an optimization again like yesterday, but then I would like to briefly show you how you can select these material models into VALIMAT. So we have implemented most of these important material models for plastics for all different solvers. So if you go into the idealization tab, so for our viewers who were here yesterday, they are very familiar now, I hope, with the model database. So this window at the bottom left. So this is exactly what we had yesterday. So if you go in one of these model databases, that is how that looks like. So we have the idealization part. And here you can specify what system of units you have, what is your solver, So we have different solvers defined here. Input deck is basically what is your validation that you want to do. So it's a 3-point bending. Is it a puncture test? Is it a tensile test? And as I told you yesterday, all of these models are predefined. So automated FE models are predefined. So symmetry of the model. We have also the idealization type, so shell or solid, and also element size. When we go back into symmetry of model, we are extremely flexible here. So for load cases where it is possible to actually have all these different symmetries, they are all well defined. For example, for a 3-point bending test, we can work minimum with a half model, and then we go further. First of with additional settings. Additional settings are basically you can define your element type. For the shell element you have selected, some extra parameters that define parameters in your automated finite element mesh. For example, the friction coefficient between the sample and the holder, for example, in a 3-point bending test. The Young's modulus of the support, the density of the support. So these are all the things that are automatically selected for you. And then we have a very important number of element layers tab, which for shell elements becomes very useful because it basically gives you how many integration points you have over the thickness. And then we go down. So VALIMAT is very easy in the sense that if you run through from the top to bottom, you can basically define your whole material model and you're ready to optimize or validate your material model. So then we go into material behavior. This is the most important. So you see material source. So they are implemented, so implemented material models. And then we have a pre-selection of all the different material behavior. So we have elasticity. So what do you want to have? A linear isotropic elastic, non-linear isotropic elastic, or a not isotropic elastic material. So if you say not, if you put it on the top to not selected, you basically get a list of everything that we have. So I would suggest my colleague put everything to not selected so we can see all the implemented material cards for LS-DYNA. So here we have a complete list. So we have the simple matte elastic, which is just an elastic material model. We have the matte 24 that we looked at in great detail yesterday. Then we have some other models, matte plasticity with damage, matte 89. And then this complicated or a very complex material model or the plastic expert, which is the matte SAMP 1. Then we have, following that, we have some material models for composites, which my colleague, Mr. Reithofer, will talk about in detail on next Wednesday. So what I suggest to do now is I will just select the matte SAMP material model because we looked at matte 24 yesterday. So after you select a material model, the most important, there are two important aspects. So one, you select your deformation behavior, and then you select your damage behavior. So when we go into deformation behavior, then we have a selection of the different yield surfaces. So so there are some yield surfaces here defined. One Mises, the simplest one. Then we have the pressure-dependent Drucker-Prager, which has tension compression asymmetry inherently defined. Then a parabolic yield surface and a general yield surface. So these are the options that the user has that he can calibrate his material model on. So I would suggest we go to a Drucker-Prager here. And then the next decision we need to make is about damage or failure. So do you want to have damage or failure in your model or you don't? So we go to add matte add erosion DM because that is something we looked at yesterday, the damage initiation evolution model. Okay, And now you've pre-selected your deformation and your damage options. So now you go into detail about your selection. So you have your hardening function. Yesterday we looked at a 4A model, new 0.5. The reason was, as I explained yesterday, we have plastic deformation at constant volume. So this is the model that defines that. But now I would want to go into detail and say, no, I want to have a plastic Poisson's ratio definition. So we have the 4A model new for that, or we have a whole host of hardening functions you can calibrate your material model on. So we select a 4A model new, for example, here, and then we get this dialog box asking us for curve 2. Then you'll be wondering what curve 2 is. Then curve 2, as I have shown in my slide just before, you can define tension compression asymmetry. And this curve 2 basically is a scaling of your tension curve to your compression curve. So here the curve 2 basically gets out. So you can either define this curve new, or you can, for maybe an easy implementation, say, I would like to just scale my curve 1, for example. It's an easier way to go around it. It's easier to understand for a first-time user to go through the software. Then we have the strain range up to and the sampling points, which I've told you before yesterday was about having the right length of the hardening curve for your application. Because it doesn't, if it's too short, then the internal solver interpolations come into play. We don't want to have that. We would like to be as accurate as possible with our strain range definition. Then you have said, yeah, I've defined my hardening function. Now let's define for a plastic the most important parameter, the strain rate dependency. Again, strain rate dependency, we have different models incorporated. So Johnson-Cook, the very popular model for strain rate extrapolation. So we go select Johnson-Cook, the strain rate dependency based on plastic strain, the formulation, or you can also use total strain formulation. So, and then you can define all your different strain rates. And now you have closed your box, or you have checked your list of deformation. So now we have defined everything under the tab deformation for the polymer. Now we need to define damage. And under damage, under ductile damage settings, we have again different functions defined automatically. Then we can select a function, for example, a piecewise linear or a Johnson-Cook or a Moore Coulomb model. So we choose piecewise linear, and this is very familiar from yesterday. We can define it stage-wise as a function of the triaxiality. So, and then the next important part is to define your load case. So what load case you want to validate or optimize your card on. In this case, we have 3-point bending. And now we have gone completely from top to bottom, and we have defined our material card. So then we hit save, right? And now when you go into design variables from material, the tab, here you see a list of all your different parameters. And the parameters that you need to define, you need to optimize, are all listed here with and they are sorted very well with names. So you have hardening, strain rate dependency, group number, failure with a failure at different triaxiality levels. And then we have our failure strain rate and the post-failure options. So I hope now each of you, if you get a version of VALIMAT, hope each of you would now be confident enough to build a material model on your own to validate it. We're all set now. Okay. So this was just a demonstration of the flow of how you select a material card in VALIMAT. So now going back to my presentation. A small summary of what we did yesterday with MAT24. So again, the same introduction of MAT24. What was our optimization strategy for the Autofit? We went through each and every step. We defined each and every step, and then we ran an Autofit yesterday. Well, that gets out a final MAT24 material card. So just a brief overview on the workflow for material card generation. We have our hardening step. Then the strain rate dependency step, followed by the validation of the material card, which results in our material model. As you see on the right here with stress over strain, our resulting yield curve. So this is what we did yesterday. After that, we looked at all our different validation results. We validated the generated material card with puncture test, with a tension bending test, and with a tensile test. Then we set up simple failure based on the failure evaluation option in VALIMAT that takes into account the failure from the test data. So by this setting of the failure time. So simple failure approach where we had a mat add erosion DM material model. We had no failure under compression and up from 0.33. So the complete tension side was set to one averaged value, where the failure strains were averaged out for all the different tests that were conducted. Okay, so after we did set up the failure, then we looked at an additional functionality in VALIMAT where we can generate an auto report. So we did a live demonstration of where we had a PowerPoint template prepared for measurement and validation results for all the different tests conducted. So we have a screenshot basically from that PDF that was generated. So we have the measurement results nicely summarized in one slide where you just look at the slide and you know how the material behaves. And then a validation results overview where again, it's just with one look, you can basically tell how the material model is performing. So that was a brief summary. On more complex material models, we will talk a lot more next week on the advanced topics. So there are 2 sessions that are planned. I will give you a small overview on those 2 sessions after the break. So I would suggest we take a small coffee break for about 10 minutes, and we come back where one of our colleagues will give you a short sneak peek into the new VALIMAT version. So what are the new features? What can you expect? What have we done more to make VALIMAT even more user-friendly? So thank you all, and I will see you after the coffee break.
Hello, everybody. My name is Benjamin Hirschmann. I work at For Engineering as a method developer. It is my pleasure today to introduce you the upcoming features of VALIMAT 3.8, which are mainly implemented by my colleague Mr. Berhard Dieker. So first step is an overview about the new features. First one is a new software installation and automated update feature. Then we have implemented Python 3.h, which will be delivered with our software. The next step, the next new feature is some extended auto report possibilities. Then we have the new Autofit failure parameter evaluation, a quick filter shortcut, then a reload parameter model button, some warning for changing networks, and a possibility to plot time-scaled curves in simulation time. So, first step is our software will now be provided via a batch script. So you will send us some data over your local system. We will create a batch script which we will send to you. You can basically place it onto the desktop and then start it. The first call will start the installation of VALIMAT, which will then be installed to users username roaming local, also app data local roaming, also app data local VALIMAT, and for example, you will see then this command window view where where you will see the progress of the download. The next step is if VALIMAT is installed, or you reopen or you will want to reopen VALIMAT, then you click this batch script again, which will close shortly after, and will start the VALIMAT starting process, which may take a while. So please be a little bit patient. So then VALIMAT will check if a new version is available, and then asks the user if you want to install the new version now. So if you accept it, you will get a progress bar, and after that VALIMAT will be updated. So a new major feature of the new VALIMAT version is that it will ship with Python 3, which will be installed in a subdirectory of your VALIMAT directory, and it will be Python 3.83 as the last versions are at the end of service lifetime and will not be supported anymore. And if you take a look at the directory in your Python installation, you will have the packages containing the modules, then the Python 3.83 executable, and also the script directory with internal and external, and basically another directory for your script. And this new Python will have a VALIMAT module, which will allow for better access to the VALIMAT database, all the curves, and so forth. The next step, which was improved, was the auto report feature. It has been greatly enhanced. So, for example, we added support for indexing for tables and text boxes and images. You will shortly see an example for that. We can now access the design variables and format them. And we can also add date and the format can be seen in the link below. So, for an example, if you want to make an overview about our MATS24 Autofit procedure, we can now add basically all the test curves at the an image of the test curves which are linked in the first model with index 0, index 1, or no index, which is then the first selected model. Then we can index the second model for the Young's modulus, the third model for the string hardening, and then the fourth model for the string rate dependency, and then for the validation. To the right side, you can access the corresponding design variables and format them with basically 0 or 2 decimal places. And you can also access the table of the validation case and add the date. So if we execute this with VALIMAT, we can have now a nice overview over our fitting procedure. Next step is an automated failure parameter evaluation. This can be added into the Autofit workflow. There you will create a failure evaluation model which will basically make a validation of all the found parameters from the previous workflow, as you see here. So you have fitted your card, then add this validation step, and in this validation step, with no failure model selected, the failure times of the measurements will be then, so the element information as the failure times will then be looked up by the script, and then the failure model parameters will be fitted to these points. And the fitted failure parameter values are then available as design variables in the steps below. So next convenient thing is a quick filter shortcut. You can add filters by pressing Alt and the left mouse button. For example, if you want to select all or view only one element or more complex models, you can Alt LMB onto this field in the database, and then the filter will be placed. Next step is a reload parameter button, which allows you to reload the model. So, for example, if you have cleared all curves in your right view, you can now go to the left side to the reload button, click it, and then get your curves back, or design variables, and anything else, as if you have just reopened the model. The next part is we had a warning because if you have a database on a network drive and you change your wireless LAN connection to this database, under some circumstances the database could be corrupted. So now you will get a text message from VALIMAT to please reopen the database. Next feature is came from a user. It was a requested feature as, for example, you have you have static tests which you calculate explicitly with a time scaling factor. For example, matsemp in some older versions is only implemented for explicit. If you then have the same time scaling factor as the difference between these tests, then you can plot now the simulation time instead of the real time to make a comparison in your force time curves or your displacement time curves. If you select in your model the plot timescale curves and set it to true. It's a somewhat improper but convenient method to compare these kinds of models. So another thing that has been added was a subdirectory in the VALIMAT installation folder. If you add there some specimens in the correct subdirector structure, you can overwrite the implemented VALIMAT measures of these cases. So, for example, you can change the puncture test specimen mesh for DYNA models. And the element sizes you can choose are 0.5, 1, 2, or 4 millimeters. So the next thing is we added a new test type to VALIMAT. So now our component bending test with a double X-rib reinforcement is now included in the test section, and if you select it, you can also simulate it with these measures, which follow the same naming convention as the user-defined. So the user-defined measures from before. So this is the end of the new features overview. There have been some bug fixes and so forth, but these are the main new features. Well, thank you for your attention and goodbye.
Hello, everyone. Sorry again, we had some audio issues. So thank you, Benjamin, for the really nice presentation on VALIMAT 3.8, the new software version. We can't wait to work more with it, and looks like VALIMAT user-friendly. So VALIMAT has gotten more user-friendly than usual. Okay, so what I would like to do now is give an outlook on the upcoming week. For the next week. So on Tuesday, we have another interesting talk by Stefan on the typical evaluation methods and interpretation of test results. So he will go into much detail on interpreting test results, on how to evaluate them properly, how to set up the correct failure evaluation, because as I mentioned yesterday in my talk, this is a very important part also of testing that will help us a lot in the modeling part also. Stefan will also show us live again from the lab the high-speed tensile test that we have on the impetus. I hope I hope all of you can join us again for this very interesting session. And what Stefan will also deal with is a question that has come up from the audience, that how do we import extra, so how do we get external test data into Impetus? Can we work with that? Yesterday, I had a small question. I said, yes, we can work with that. And Stefan will give us a live demonstration of how to actually do that in the software. On day 6, the 15th of July, we have a very interesting talk from Benjamin and Peter on the Autofit workflows for a complex material model. In this case, we will be looking at the MAT-SAMP material model, where they will go into great detail on explaining what this material model is, what can it do, and how do you use the test data to calibrate the material model using the Autofit workflow. It will be shown live. Again, as I have done for MAT24 Autofit, it will be shown live in the software. So this should also be a very interesting session for next week. And at the end, we will do a validation on all the conducted tests. And the other important aspect here also is that we will take a look, deeper look into setting up complex failure. Because yesterday I did a simple failure with no strain rate dependency. But next week we will go into greater detail over setting up failure with strain rate dependency also. And on day 7, we deep dive into fiber reinforced thermoplastics, the different modeling guides, techniques, how you can use VALIMAT to also make modeling fiber reinforced thermoplastics also much easier. This will be a topic that will be dealt with by Mr. Peter Reithofer. On day 8, we jump into jump into the software again, VALIMAT. We deal extensively with user-defined specimens, user-defined input decks and material cards, which was also a very requested question from the audience on how do we incorporate new materials into VALIMAT and how do we work with that. So this day will be interesting for all of those who want to know how do we customize VALIMAT to incorporate all these different material models. What is also another interesting topic for that day would also be possibilities in VALIMAT with Python. So VALIMAT is already capable of doing a lot of things in an automated manner, but when we couple Python to it, so some extra functionalities can be added in VALIMAT, which would greatly help with the process of either be material card generation or to evaluate tests in a better manner, or to even do simple things like create a video from high-speed tests and everything that can be integrated with Python. So this brings me to the end of the session today. And what I would suggest now is that we have a Q&A session with all the members of our team. They are all present here today. So from testing, from simulation, and also from our software development. So we would be glad to answer any question you might have with the specialists from these individual fields. So thank you again. Thank you for your attention, and I wish you a very happy weekend. Thank you.